Okay, we're going to start with an introduction to optical mineralogy. And we can do this in just a few lessons on the microscope, the petrographic microscope, how it works, how light is transmitted through it, what we see in thin sections, and how we can use the properties, the optical properties of the minerals to identify them. In these lessons, we're not going to be identifying any minerals. We'll do that later. For now, it's just an introduction on how it works and how to identify those optical properties. Okay, so this module is about the petrographic microscope. You might also hear it called a transmitted light microscope, and how light passes through it, how we identify color in thin sections, and pleochroism. So first of all, why are we using the microscope at all? It allows us to identify minerals without having really to guess. If you're looking at a rock or a mineral specimen, sometimes you have an idea what it might be, but sometimes if it's not displaying the right physical properties, it's hard to know for sure. So looking at minerals in thin sections, we can get more information from the optical properties that oftentimes allow us to identify it 100%. When we look at a particular assemblage of minerals in a rock, like the different minerals you see in this image here, it tells us what kind of rock type it is. Maybe we can find out something about the order in which different minerals crystallized, or something about how the rock was deformed over time. We can see mineral reactions frozen into the rock too. So we might see evidence if a rock, let's say, comes from a subduction zone, was subducted to some point where it was at very high pressure and temperature, and came back to the surface where we collect it, that rock can record a lot of different metamorphic events over that history. So we can see those reactions, and we can establish a pressure and temperature history for the rock. We also see things like weathering and alteration, and it's relatively inexpensive and easy to make a thin section. And if you have a microscope, it's you get a lot of information out of thin sections. All right, this is a slightly blurry image of a petrographic microscope, but it's got all the relevant parts that I want to show you labeled. And I have a note here to remind you it's also called a polarizing microscope. So you'll hear interchangeably petrographic microscope, polarizing microscope, or a transmitted light microscope. Transmitted light just simply means that the light is coming from the source at the base of the microscope and shining light through whatever it is that you're looking at. So it doesn't actually tell you that that's necessarily a polarizing microscope, but petrographic microscope, you assume it is. All right, the parts of the microscope. This happens to be a binocular microscope. It has two eyepieces that you can look through, two oculars. A lot of the microscopes in our classroom are monocular microscopes, and those work just as well. Let's start at the base of the microscope, down here by the light source. Most of the microscopes in class have a power switch for the light, and they have some way, a knob or some adjustment to change the light intensity. So you can use low light up to very bright light to shine through your microscope. Down here below the stage, a couple of important pieces. The lower polarizer, so all the light that passes through the microscope is polarized once at least. Above that is the condenser lens that you can use the little knob on the side of beneath the stage to put that lens in or take it out. Then we have the stage itself, where your sample sits. And on that stage is markings for 0 to 360 degrees. So you can, for instance, record how much you have to rotate the stage in order to see a particular property, like when a mineral goes extinct, that we'll talk about in a later module. Then we've got the objectives. here. And most of the microscopes have 3 objectives: a low, intermediate, and high magnification objective, perhaps 2.5 times, maybe a 10 times or 25 time magnification objective, and the highest power is usually about 40 times magnification. Above that, we have the upper polarizer that you can put in or take out to decide whether or not you want to look at in plain light with the upper polarizer out, or in cross-polarized light by putting that upper polarizer in. Up there we've also got the accessory plate that you can put in or take out. Most of the time it will be out. We won't use the accessory plate for the most part when looking at thin sections. And that's usually gypsum. And then above that, here it doesn't show the knob on the side of your microscopes. That is the Bertrand lens. That's another lens that we use for a very specific reason that I'll get into later. So, in order to use the microscope, we need to understand a little something about how the physics of light works and some of the tools that we use. Before I insert the microscope, this is basically what's happening. You've got a light source at the bottom of the microscope, and your eye is looking down the microscope. The light is traveling as waves from that light source, and it's white light. It's composed of many different wavelengths of light traveling in all different directions. And all of those wavelengths of light have a particular amplitude and a particular wavelength. And as I said, there's many different wavelengths of light coming toward your eye at once. You recall that you already know that white light is made up of many different wavelengths of light, because if you pass white light through a prism, you can separate out the different colors into red, orange, yellow, green, blue, violet, and see those, prove to yourself that there are all those different wavelengths there. In the petrographic microscope, all of the light is polarized, which means that we're only taking light that's vibrating in a single direction or a single plane. In unpolarized light, if there wasn't that lower polarizer there, you'd have light that was traveling in many different directions, many different planes, toward your eye. So, again, looking at the light source, at first it's emitting unpolarized light, but in the microscope we have a lower polarizer that filters those wavelengths of light and gives you only a single wavelength of light that actually could reach your eye. And when that happens, you're actually reducing the light intensity. And when you're using the second polarizer and when you're using higher magnification objectives, you actually need to increase the intensity of the light so that you can see through the thin section easily. All right, so we've got the unpolarized light passing through the polarizer, leading to a single light vibrating in a single plane. Then we have to introduce the upper polarizer. And the upper polarizer is oriented perpendicular to the lower polarizer. And if we do nothing else, and you can prove this to yourself on the microscope, if you put the upper polarizer in and you have nothing on your stage, what you see through the eyepiece is black. It's extinct. So you filter out all wavelengths of light when you do that. So why would you design a microscope that actually blocks light from getting to your eye? The last component that we'll incorporate into this model is a thin section of rock. When you insert a thin section of rock in between the lower polarizer and the upper polarizer, we see something very different. What reaches your eye are interference colors. What's happening is that the minerals in the rock are reorienting the light and sending many different wavelengths again, passing through that upper polarizer to our eye. How's that work? I can reinforce that minerals reorient that light and the planes in which the light is vibrating. And some light passes through the upper polarizer. So if we're looking in plain polarized light, so with just the lower polarizer and the upper polarizer out. I'll also abbreviate that PPL for plain polarized light. You see the color of the minerals. In this case, they're all colorless. When you insert the upper polarizer, also I'll use XPL, so cross-polarized light, you see interference colors. So the minerals themselves are changing the way the light is passing through that upper polarizer, and we see those interference colors. So this goofy graphic to suggest that the minerals are doing some work to change what we're seeing in the scope. And some minerals do this better than others. There are some minerals, isotropic minerals, that can't reorient the light, and I'll talk about that later too. All right, so specifically color and pleochroism here, those are two properties that we can only ever assess in plain polarized light, in PPL. This depends on the particular minerals. Not all minerals have a color when you pass light through them, and not all minerals that have color are pleochroic. And pleochroism is a property whereby you have a colored mineral. In this case, on the left, we have hornblende in browns and greenish browns, and plagioclase that is colorless. If you rotate the stage, and the right-hand image is rotated by about 90 degrees, you'll see that the color of this grain of hornblende changes from light brown to a dark brownish green. The fact that the color changes in intensity is the pleochroism. So you have to, number one, have a mineral that has color first in order that it might be pleochroic. And many minerals that have color aren't pleochroic. So that's an important property to have. Biotite's another example of a pleochroic mineral. It's very common in the rocks that we'll look at. These are two images that are rotated by 90 degrees, and you'll see that in the upper left-hand image, the biotite has a dark red, reddish-brown color, rotated 90 degrees, and the color is much paler, so a light brown. That's pleochroism and color. So what you learned in this module is that minerals reorient light that is transmitted through them, that the color of a mineral is only seen in plain polarized light. The colors you see in cross-polarized light are interference colors, not just color, but interference colors, or we call that birefringence. If a color of a mineral changes as you rotate the stage, this is called pleochroism, and the mineral is pleochroic. So to test what you've learned here, go and watch videos of thin sections 8 and 99. I would have a pen and paper in your hand so you can take notes on the videos. And then I want you to complete the quiz on color and pleochroism.